The equilibrium constant for the reaction of 2 moles of nitrogen monoxide reacting with bromine to make 2 NOBRs is 1.3 times 10 to the minus 2 at 1,000 Kelvin. At this temperature, does the equilibrium favor the nitrogen monoxide and the Br, or does it favor the products, the NOBR? When you have a K value smaller than 1, this means it's a non-spontaneous reaction and it favors the reactants, meaning this reaction doesn't go very far forward before it stops. So you have a lot of reactants left over and very few products made. B, calculate the Kc value for the reverse reaction, right? So turn the reaction around. Put 2 moles of NaOBr turning into nitrogen monoxide and bromine. If you turn the reaction around, a reaction that's non-spontaneous in the one direction is now spontaneous in the other. So to get the magnitude of the K value, we take the inverse of the K value. And that would give me a number larger than 1. So non-spontaneous in one direction means spontaneous in the other direction. And C, calculate the Kc value if I have 1 mole of NOBr, making 1 mole of NO and half a mole of bromine. If I divide the reaction by 2, right, to make it, instead of 2 moles, making 2 moles and 1 mole, I'm making 1 moles react to make 1 mole and half a mole, I take the equilibrium constant to the 1/2 power. And that would give me the new K value for the different balancing. So coefficients matter in equilibrium expressions. The following equilibria were attained at 823 Kelvin. Cobalt 2 oxide reacting with hydrogen to make cobalt and water. Cobalt 2 oxide reacting with carbon monoxide to make cobalt and carbon dioxide. Both of these reactions have spontaneous equilibrium constants. Based on these equilibria, calculate the equilibrium constant for hydrogen reacting with carbon dioxide to make carbon monoxide and water. Okay, so we dealt with this before with thermochem, right? If we add equilibria together, we can come out with an overall equilibrium. Whatever I do to the equation, I had to do to the delta H. So in this situation, whatever I do to the equation, I have to do to the equilibrium constant. So I look at the equation I want to get to. I want to get to hydrogen reacting with carbon dioxide, where both of those are in the reactants. So if I look at the first equilibria, I've got hydrogen in the reactants, so that's good. And I want 1 mole of carbon monoxide in the reactants. So that means I've got to carbon dioxide in the reactants. So I've got to turn the equilibrium around for this second equilibrium. So if I turn it around, right, spontaneous in one direction, non-spontaneous in the other direction, right? So I take the inverse of the K value when I turn it around. So now I've got hydrogen and carbon dioxide going in as reactants. Cobalt solid will cancel, cobalt 2 oxide will cancel, and I'll be left with hydrogen reacting with carbon dioxide to make carbon dioxide to make carbon monoxide and water. So when I add equilibria together, what I do with the K values is multiply them. So if I multiply K1 times K2, I get the overall K value. And I get a non-spontaneous reaction. All right, so as we could see, right, the one reaction was way more spontaneous than the other one, so therefore it's way more non-spontaneous going in the reverse direction. So this is how we deal with multiple equilibria. If we have to add equilibria together to get an overall equilibria, I multiply the K values. 34. Gaseous hydrogen iodide is placed in a closed container at 425 degrees Celsius, where it partially decomposes to hydrogen and iodine. Okay, so we have the equilibrium. At equilibrium, the hydrogen iodide concentration is found to be 3.53 times 10 to the minus 3 molar. The hydrogen concentration is 4.79 times 10 to the minus 4 molar. And the iodine concentration is 4.79 times 10 to the minus 4 molar. What is the value of Kc at this temperature? All right, so in order to get the K value, We take these concentrations at equilibrium. Again, these are the concentrations when the reaction stops. So when the reaction stops, I look at this and I seem to have more reactants left over than I made products. So this would appear to me to be not a spontaneous reaction, meaning I'm going to have a small K value. Small meaning less than 1. So I take these concentrations, plug them into law of mass action, right? The concentration of the reactants, raise their stoichiometric coefficients, divided by the concentration of the the concentration of the products, raise their stoichiometric coefficients, divided by the concentration of the reactants, raised to their stoichiometric coefficients, and solve for Kc. The prediction is it's going to be smaller than 1. And I was right. So we didn't make very many products before this reverse reaction took over and stopped the reaction, and we got these concentrations. At 100 degrees Celsius, the equilibrium constant for a reaction of CoCl2 reacting to form carbon monoxide and chlorine has a K value of 2.19 times 10 to the minus 10. Again, not very spontaneous. Which of the following mixtures, are the following mixtures at equilibrium? If not, indicate the direction at which the reaction must proceed in order to achieve equilibrium. All right, so given these concentrations, right, with the set of concentrations in A, I want to know if these are equilibrium concentrations. So what I do is I take these concentrations, plug them into the law of mass action, and solve for the value. Now we're going to call the value with what we call this value is the reaction quotient, Q. And then we compare that value to K. If Q is bigger than K, which is the case here, this means you have too high a product concentration and too small a reactant concentration. You've gone too far forward. This reaction has to shift backwards in order to get to equilibrium concentrations. So I've got to lower that 3.3 times 10 to the minus 6 and that 6.62 times 10 to the minus 6 concentration and raise the concentration of the reactants in order to get to equilibrium concentrations. So when I do the same thing with the set of concentrations for B, plug them into the law of mass action and compare Q to K. In this situation, Q is less than K. So I haven't gone far enough forward. This reaction's still going forward with these concentrations. I've got to lose some more reactants, make some more products in order to get to equilibrium concentrations. So this is what this information gives me. With these concentrations, I'm not at equilibrium. I've still got to go forward. With the concentration set we're given for C, when we plug it in and solve for Q, I get the same value as K. So what this tells me is the reaction stopped. I'm at equilibrium. These are equilibrium concentrations. So I'm not going to lose any more reactants and make any more products. And this is it. This is what I'd have at equilibrium. At 900 Kelvin, the following reaction has a Kp value of 0.345. An equilibrium mixture, in an equilibrium mixture, the partial pressures of sulfur dioxide and oxygen are 0.135 atmospheres and 0.455 atmospheres, respectively. What is the equilibrium partial pressure of sulfur trioxide in this mixture? All right, so in this situation, I've got 3 of the 4 variables. I know what my reactant pressures are. I know what the Kp value is. What I don't know is the product pressure. So I treat X like it's the product pressure, plug it into the law of mass action, right? The concentration or the pressures of the gases raised to their stoichiometric coefficients, and solve for X. X will be the pressure of sulfur trioxide. So we solve for the missing number here. In 51, 2000 degrees Celsius, the equilibrium constant for the reaction of Nitrogen monoxide reacting to form nitrogen and oxygen has a Kc value of 2.4 times 10 to the 3. If the initial concentration of nitrogen monoxide is 0.175 molar, what are the equilibrium concentrations of NO, N2, and O2? All right, so this is a classic problem, right? We want to know what the equilibrium concentration is going to be if I'm starting with a certain concentration of the reactant. So this is my setup. I've got a very spontaneous reaction where I have a certain concentration of my reactant, so I expect that concentration to go down and the concentration of the products to go way up. So the question is how much of the reactant am I losing? Well, according to the stoichiometry, for every 2 nitrogen monoxides, I'm making 1 nitrogen and 2 oxygens. So for every 2x, right, I'm losing X amount of nitrogen monoxide. It's going to be a lot. The relationship is for every 2x of NO lost, I'm making X amount of N2 and X amount of O2. So these are my equilibrium concentrations. I take these concentrations, plug them in the law of mass action. So X times X, right, raise their 1 power is X squared, divided by the initial concentration of nitrogen monoxide, subtracting 2X, raise the second power. All right. And I solve for X. Now, a lot of times with these problems, you end up having to solve for a polynomial, right, using the quadratic equation, and we want to avoid that. And on the AP exam, they're not going to give you a problem where you have to solve for quadratic. It just takes too much time. So they usually give you problems where you can use some sort of trick, where you don't have to solve for a quadratic. So in this situation, I look at this, and I can see that if I take the square root of both sides, I can get rid of the squared term in the numerator and in the denominator and make this a lot easier to solve for, so I don't have to solve for quadratic. So I just want to collect terms at this point, right? So multiply both sides by 0.175 minus 2x. All right, and I get 8.573 minus 97.96x is equal to x. Collect terms, so add 97.96x to both sides, all right, and you get 98.96x. Divide both sides by 98.96, and I get x. And that is the equilibrium concentration for the nitrogen and the oxygen. The equilibrium concentration for the NO, you'd multiply X by 2 and then subtract it from your initial concentration. So as we thought, right, the concentration of the reactants is going to be way down compared to the concentration of the products. So that's what it means to be a spontaneous reaction. Very little reactants left, more products formed.